Okay, so number 18 and 19 are actually a little easier questions in a sense, other than the fact that number 19 has the dreaded logarithms and you got to remember some of those properties. They're not too bad. So let's kick that one off here and see what happens on those. So we're looking at some composite functions here where we're plugging something into one function and then getting a result and then choosing that result to then plug into another. So let's see what happens here. So if we were to find g of 2, I'm not going to actually show that work, but g of 2 clearly is 4 minus 1 is 3. So again, since this value right here is 3, I'm just going to replace that with the number 3, plug it into here, and we're going to get root 3. Easy, moving on, no big deal. Now, a lot of people think of the commutative property, how you can move things around, you just get the same answer, but that's completely not true when it's coming to composite functions. You know, if you put your stuff in the blender and then you put it in the oven, it's very different than if you put it in the oven first and then the blender second. So sometimes the order in which you do things matters. So if we plug in the 2 right here, f of 2 is root 2. So then I need to take g of that. So I'm going to take root 2, square it, and subtract 1. And clearly I want very different answers because of the differing order. In this next one, we're going to say f of negative 4. Now, sometimes people like to write no solution because, oh, I'm taking the square root of negative 4. But can we actually do that? And we all know that you can take the square root of a negative, but I'm going to say not a real solution. That actually does mean that we could get one, but I will tell you calculus is really not all that interested in the imaginary part. A lot of times calculus goes by a whole lot of different names. Sometimes call it analytic geometry. Sometimes we just call it calculus. Other times we'll call it real analysis. So it goes by a couple of different names. So like this negative created problems for me. But what happens if we go in the other order? Well, g of negative 4 would be 16 minus 1 is 15. So now I'm looking for f of 15, which is, of course, root 15. That was pretty simple. But now the last one is like saying, hey, can I just do a one-stop shop and not do it in stages? Can I just go find the master function? So I'm going to take f, which is this outer function. F was the square root of x, but I'm going to replace x with whatever g happens to be, and I'm done. And in the same way over here, I'm going to take g, which is x squared minus 1. Those that haven't had me before, when I evaluate functions, I take the value, I make an open parentheses, I wait to plug it in until I've expressed my whole thing, and then I plug in f into that little hole. Now, this is actually something that a lot of math students will make a mistake with, because this is claiming that this value is x minus 1, because obviously the square root squared is x, but it isn't. Because when I do all of this, I cannot change the domain of a function, and I have. This makes it look like I can plug in any value of x that I want, but we clearly know that there are some limitations to that because I couldn't do it over here. Wait, where was it? Right here. I couldn't do it. So what is wrong? There's only certain values that I could plug in for f to make it work. So that's a little bit interesting. So what it is you have to go ahead and you take the intersection, you consider your final answer, which this domain would be all reals, but you also consider the interior function, this guy right here, where x has to be greater than or equal to 0. So this is true, but I need to make a little note that the domain of my answer here is x values that are at least 0. Okay, this is a valid answer, but only a valid answer in the case where those values are 0 or up. Now, number 19, pretty easy. You actually saw something in a previous video where we talked about properties of logs, but the definition of a logarithm says that the base of the logarithm, I wish I wrote that a little bit nicer, comes across and becomes the base of the exponential. And so this 3 pops across, and it's 3 raised to the 9/2 power. Or in other words, you could say the half power is a square root. It is a square root of 3 to the 9th. Either one of those values would be considered legitimate, okay? Now moving on to letter B, the last one for this video. I told you this one wouldn't be too bad. is we're going to move things around just a little bit using some properties of logs. First off, I'd like to make sure that all of my logarithms, when there's multiple logs, have the same base. And you're going to see right here that they are. So that's a happy thing. I don't have to use the change of base formula. I do, though, want to express each of them as a simplistic log. So this is really not 2 log 3 of 4. It's actually log base 3 of 4 squared. Over here, this is the log base 3 of 5 raised to the 4th power, which is 625. Now, one of those nice little properties of logarithms is when you subtract, it's just properties of exponents. When you divide things, you subtract exponents. And since logarithms point us to properties of exponents, that's what's going to happen here. That's going to be the log base 3 of the simple quantity of 16 over 625, which is pretty good. So we have a simple log, a simple log. So if the log of something is equal to the log of something else, those two values would then clearly have to be the same. Now, again, there may be a couple of different ways to do this problem, but I felt like that was pretty efficient. So I'm not looking for x squared, I'm looking for x itself. So if we take a quick square root of both sides, we're looking at 4/25, and we are out. Pretty nice, easy little questions if you remember a couple of properties. All right, see you later.